Welcome to the today's video lecture series. In last class, we had been discussed about the constructional parts of an induction motor. In today's class, we are going to see about the working of an induction motor, which comes under the course outcome 3 to exemplify the electric propulsion system and motor controlling techniques, under which the learning outcome 1 is to discuss about the electric propulsion system, under which the specific outcome 2 is to explain the construction and working of an AC motor, that is induction type motor. The content of the today's presentation has been associated with operation of an induction type motor. So the operation of the three-phase induction motor. So the main essence in the operation of the three-phase induction motor is whenever the three-phase AC supply is being given to the stator windings of the induction motor, then the rotating magnetic field will be developed from the stator winding. The stator winding is stationary only, but whatever the magnetic field is developed from the stator winding is rotating in nature, so which is of the synchronous speed. So field is that this field is such that the poles do not remain stationary on the stator, but they go on shifting. But as it is a three-phase AC supply is applied to the stator winding, the north pole and the south pole of the developed magnetic field on the stator winding will be varying. For this reason, it is said to be the rotating magnetic field. So this rotating magnetic field will be rotating in terms of the synchronous speed. That means synchronous speed is indicated by ns, which is equal to 120 F by P, where F is said to be the number of the poles on the stator and F is said to be where P is said to be the number of the poles on the stator and where F is said to be the supply frequency. Next, so direction of rotating magnetic flux produced from the stator. The direction of rotating magnetic flux depends upon the phase sequence of the supply voltage. So if any two phases of the three-phase line to the stator windings are reversed, then automatically the phase sequence is also being reversed. So this reversing the direction. So this will reversing the direction of the rotating magnetic field, that is RMF. Next, principle of operation. Consider a three-phase induction motor, which is shown in the next slide figure. The operation of the three-phase motor can be explained when the three-phase stator winding is energized from the three-phase AC supply. Then the rotating magnetic field is developed or is set up in the setup whose speed is about the synchronous speed, which is ns is equal to 120 F by P, where F is a supply frequency, P is a number of the poles in the stator. So the rotating magnetic field will passes through the air gap and it will cut the rotor conductor. So as per the concept of the electromagnetic induction, whenever the rotating magnetic field cuts the rotor conductor, then automatically an EMF will be induced in the rotor conductor. So we know that the rotor conductor are short circuited by means of the copper bar or an aluminium bar if it is a squirrel gauge induction motor. So due to which whenever an EMF is induced in the rotor conductor, then the short circuit current will flows through the rotor conductor. So due to the current flowing through this rotor conductor, the rotor also develops a magnetic field. So now after the rotor develops a magnetic field, then it resembles when the current carrying conductor is placed in the magnetic field, which is a rotating magnetic field produced by the stator. So due to the rotor magnetic field and the rotating magnetic field developed by the stator, that is a rotating magnetic field. So due to the interaction of both rotor magnetic field developed on the stator and the rotating magnetic field developed on the rotor, due to the interaction of both the rotating magnetic field developed on the stator and the rotor magnetic field developed on the rotor conductor, there is a mechanical force or a mechanical torque will be produced in the three-phase induction motor. So this is a rotation of the stator field whenever the three-phase AC supply is applied to the stator winding. So whenever there is a three-phase supply applied to the stator winding of the three-phase induction motor, then the RMF, rotating magnetic field, will be produced. So due to this RMF, there is a magnetic flux lines is passing from the from this direction, from top to bottom direction. So this is said to be the air gap. This is said to be the air gap. So this are said to be the rotor conductors. So when this magnetic flux lines cuts this rotor conductor, due to the electromagnetic induction, Faraday's law of electromagnetic induction, an EMF will be produced in this rotor conductor. We know that this rotor conductor are short circuited by the copper bar or aluminum bar. So current is flowing through this rotor conductor. Again, there is a MMF, that is magnetomotive force, developed by this rotor conductor due to the current flow. So this rotor MMF, that is a rotor magnetic field, and the rotating magnetic field produced by the stator will get interact each other, due to which there is a mechanical force or a torque developed in the rotor conductor as same direction of the stator rotating magnetic field. Next. So this is a fact. According to the Faraday's law, according to the Lenz's law, the direction of the rotor current will be flow in such a direction that it tend to oppose the cause producing it. Now, the cause producing the rotor current is the relative speed between the rotating magnetic field that is produced by the stator and the rotor conductor magnetic field produced by the rotor, that is said to be the slip. That is slip is rotating magnetic field which is synchronous in nature ns minus the rotor conductor rotor speed, actual speed of the rotor nr. So this relative speed difference, or speed difference is said to be the slip. So now the cause producing the rotor current is the slip, that is a relative speed between the rotating magnetic field produced by the stator and the stationary rotor conductors. Hence, to reduce the relative speed, that is slip, the rotor starts running in the same direction as the RMF developed by the stator, and it is trying to catch the RMF, rotating magnetic field speed. Next, so slip, as I told, that it is a difference between the synchronous speed ns and the rotating field, synchronous speed ns and the actual rotor speed n divided by ns. So it is a difference between the rotating magnetic field produced by the stator, which is a synchronous speed, and the actual rotor speed. So these two difference are said to be the slip, or simply it is said to be the relative speed between the synchronous between the RMF developed by the stator and the actual rotor speed. So percentage of slip S is equal to NS, that is RMF developed by the stator minus N, that is actual speed of the rotor, divided by NS. Again it is RMF developed by the rotating magnetic field, RMF developed by the stator, into 100, as it is a percentage slip. Next, so when the rotor is stationary, that means the rotor speed is 0, then slip is equal to 1, or simply it is said to be 100%. In an induction motor, the change in slip occurs from no load to full load is hardly between the 0.1% to the 3%. So this is what an idea regarding the operation of the three-phase induction motor. I hope that you would be understood. Thank you.